Today I'm going to be going through a vectors question that I found particularly interesting. I sat this in an assessment a few months ago. I'm just going to go through how I solved it. So, we're going to start with an octopus. Yes, an actual octopus that we're going to model as a particle. And this octopus has the ability to catch a fish that comes within 2 meters of its surroundings. Now, this means that in 3D space, it has a sphere surrounding it, which, if a fish passes through, the octopus can catch it. We're actually given the path of a fish that's going to pass near to where the octopus is, and we're asked whether the octopus can actually catch the fish. We're going to model the path of the fish as a line, and the vector is going to have 3 components, x, y and z, corresponding to the 3D Cartesian coordinates. So I've drawn the line outside the circle, but actually we don't know if it passes in or outside the circle. And because we're trying to find out if it does, we should model this line as a vector equation and turn it into a vector form. And we can do this just with subtraction. If we subtract this vector from this vector, we get the vector that shows how to get from here to here, which is just this. Now we know that on this line, from any point to any other point can be, for example, this plus a multiple of this, or this plus a multiple of this. And we can write this in vector form using lambda as the preferred variable. So I've labelled this line A, and as you can see, if we started here and added a multiple of this, for example lambda being equal to 1, we would get here. And for example, say you added lambda equals to 2, well, the line would just continue in the same direction. And even if lambda equaled -1, we would just go down here somewhere. This means that we've represented the line in a vector form, and now we can start doing some maths. So, if we model the octopus as the origin, we can figure out exactly what the furthest distance away from the octopus is, and then we can test that to see how close the fish gets and compare the 2 values. And we could even simplify lambda at this point. Just to make things a bit easier, we can divide by 3. And this really doesn't make a difference because lambda is going to be a variable in its own right, and we can just kind of absorb that 3. Now I've drawn some lines away from the origin, and this is what's going to help us generalise an equation to get from the origin to the line. Now in vector notation, the distance from O to A can also be expressed as A minus O, and in this question A is just that, and O is in fact 0, which makes it really interesting and really easy to say that the distance from O to A is technically just A. As you can see, I've simplified it into a single vector. Now it's time for some vector calculus. We know that this O to A represents all possible distances from the origin, or the octopus, to the path of the fish. Now we need to minimise this, and we can just do this using differentiation. We need to express O to A in a slightly different way, and this is just going to be using 3D Pythagoras, which allows us to go from the origin to the line. And it's still going to have a variable in, but that's fine because we just want to minimise it, and we'll end up finding the variable anyway. If we minimise the distance from O to A, we have also minimised the distance from O to A all squared. And this means we can just ignore the square root for now. We can square both sides and still minimise lambda, and we're going to get the same answer. Now let's expand and simplify. Now we need to minimise this, and this is just a quadratic equation, a positive one at that, so we know it's going to be minimised when the value of DOA, d lambda, is 0. Let's differentiate. This is what we get, and it's pretty easy to see that if we set this to 0, lambda is going to be equal to 1. And what does that tell us? Well, if you remember, we're trying to minimise the distance from the octopus to the fish. And we know that happens when lambda equals 1. And we can bring that all the way back up to the top and find just the singular point at which this happens. Let's go back to the model. If lambda equals 1, we can then say we know the minimum distance from the octopus to the path of the fish. And let's just quickly work this out. And we can work out how far this is from the octopus by using 3D Pythagoras again. Root 1 plus root 4 plus root 1 again, and we get root 6 to be the answer. Now, is this lower than 2 meters? Well, we can check our calculators. Root 6 is in fact greater than 2. This means the fish is not caught. Hooray for the fish. And there are a few more questions added to the end of parts B and C, which criticise the model and allow you to think about how we could improve it. But I think that's all we got time for, and I'm going to be doing a few more questions like this in the future with the matrices and the like. Just stuff that further maths A-level students will be taught. Thanks for watching.